Okay, so I'd like to talk about a topic called dimensional analysis. Okay, so dimensional analysis is hands down the single most powerful tool and simplest that you have in your, physics toolkit for solving physics problems. Okay, so the basic idea is in mechanics courses like Physics 121, there are basic physical quantities that you can measure. So there's length, time, and mass. So length, time, and mass. And these are assigned letters. These are called dimensions, and they're assigned letters. Let's make a little table here. So the dimension of length is given the symbol L, and the dimension of time is given the symbol T, and the dimension of mass is given the symbol, you guessed it, M. Okay? Now, dimensions, length, time, and mass, are different or distinct. They're related to, but they're distinct from the units. Okay, so the units that you choose to measure these quantities, a length, a time, and a mass, the units you choose, well, you can choose make any choice. So if you used SI units, which is what we use in this course, you would measure a length in meters. You would measure a time in seconds, and you would measure a mass in kilograms. If you were using another system of units, you might measure length in inches, and you might measure time in seconds, and you might measure mass in, I don't know what they measure mass in, slugs or stones or whatever. Okay, so the units that you use to measure dimensions, depend upon what choice of units you'd like to use. They're different for different sets of units, but the dimensions are universal things. And in physics, we're interested in universal things. Okay, so we want to get used to using length, time, and mass rather than units like meters, seconds, and kilograms. Okay, so let me give you an example of just sort of notation, how we use this kind of stuff. So suppose we have a distance d, and we wanted to ask the question, what are the dimensions of this variable d? To ask what are the dimensions, you put square brackets around the variables. So this is asking, what's the dimensions of d, of a distance? Oh, well, that would be a length. Okay. If you were using SI units, you would measure that distance d in meters, but its dimension is a length. Okay, another example, common example in, say, Phys 121 would be a velocity. So a velocity has the dimensions of length over time. Now, if you were using SI units, you'd measure velocities in meters per second, but the dimensions of velocity are length over time. Another one is, say, force. So what are the dimensions of force? I don't know. But I do know that force is mass times acceleration. And so the dimensions of mass times acceleration is the same as dimensions of mass times dimensions of acceleration. The dimensions of mass, oh, that's just m. The dimensions of acceleration, that's a length over time squared. Or if you were using SI units to measure acceleration, you'd say meters per second squared. Okay? So that's force. And then suppose you have, say, some physical constants that you're trying to figure out the dimensions of. This often happens. So for instance, suppose you're trying to measure, or you're trying to figure out what are the dimensions of Newton's gravitational constant, big G. Okay, so then these things, I don't know what that is. But you do know something about it. You do know that if you have two masses, m1 and m2, separated by a distance r, then the magnitude of the gravitational force is g m1 m2 over r squared. So you know this. Force is g times m1 m2 over r squared. And so if you wanted to figure out the dimensions of g, well, just solve this equation algebraically for g. Okay, so this tells you that g is equal to f times r squared divided by m1, m2. So therefore, the dimensions of g are the same as the dimensions of force. We figured that out. Mass length over time squared times the dimensions of a radial distance r squared. Well, that's a length squared. So that's length squared divided by two masses. Okay, so that's the dimensions of mass squared. Okay, and then you can algebraically simplify this. There's a mass in the numerator and a mass squared in the denominator, etc. So you get a length cubed divided by a mass times squared. So the dimensions of Newton's gravitational constant are length cubed over mass times squared. If you were measuring this using SI units, you'd measure lengths in meters, so you'd have a meters cubed. Mass would be measured in kilograms, and time would be measured in seconds. Okay, so it would look something like that. These are the units. These are the dimensions. Learn to distinguish between those two. Okay, it's going to be really important for the stuff that we do. Okay, so here's a super simple example. Suppose you have, the kinematical equation for, one-dimensional motion under constant acceleration. So x final is x initial plus v initial times t plus 1/2 a t squared. And suppose I can't really quite remember that. Is this a v or is this a v squared? Well, you can easily check. And what you need to check is that the dimensions of every term is a length. That's a length, that's a length, that's a length, and that's a length. Because you can add lengths. You can't add apples to oranges. You can't add a length to a time, but you can add lengths to lengths. Okay, so let's just double check here. So the dimensions of acceleration times time squared, well, acceleration has the dimensions of length over time squared times a time squared. The time squareds cancel, and you get a length. Check mark. Okay, the dimensions of the initial velocity times time term. The dimensions of velocity are length over time. The dimensions of time are t. The t's cancel, and you get a length. Check mark. Okay, and obviously these guys, x initial and x final, these are positions. Okay, they are measured. They are quantities of length. So they're obviously a length. So length equals length plus length plus length. Okay, so whenever you sort of write down any kind of a formula, you can very easily check if you've made a mistake. Okay, if your dimensions don't work out, you've made a mistake. If the dimensions do work out, you not necessarily haven't made a mistake. For example, suppose you put a quarter there instead of a half. Well, the dimensional analysis is insensitive to numerical factors without dimensions like that, or a minus sign instead of a plus sign or something. You can still make mistakes like that, but at least you'll get the dimensions of all the terms correct. Okay, so that's important. Let me see. So the last thing to say about this, before we go on to a really interesting example here, is what's the real power of dimensional analysis? Why do it? Well, there's two sort of reasons why we do dimensional analysis. So one is to check your answers. Okay, and so you've already been doing this in high school. So the idea is you have some formula and you plug in some numbers. And whenever you plug numbers into a physics formula, you always include the units for those numbers. And then you cancel, meters here, meters there, and so on. You cancel out and you make sure that the units work out right. Okay, that's something that I'm expecting all of you are in the habit of doing. That's sort of like level 0. Okay, you got to be able to do that. Okay. But in this course, we're going to take that to 2 higher levels. Okay, the next higher level is to check formulas. So this is numerical, this is algebraic. So this is numerical, and this is algebraic. Because the fact of the matter is, in this course, almost all of the solutions to the physics problems that you're going to be solving, all the significant ones, are going to be formulas. They're going to be algebraic expressions in terms of the variables in the problem. And there will be very few numbers. Maybe at the very end you'll plug in some numbers to your final formula, but all of the derivations will be algebraic throughout. Okay, and so what you need to be able to do is take an algebraic expression like this or like this and be able to figure out whether the dimensions of this right-hand side is equal to the dimensions of the left-hand side, just to double check that you haven't made, a big mistake. All right, so that's that. However, the real power of dimensional analysis for real working physicists is, this is important, but much more important, and as I said, this is the single most important, most powerful tool in your physics toolbox for solving physics problems, is that you can estimate, you can come up with solutions to, or estimates to solutions of problems that you could never do without much more advanced physics. Okay, so you can solve really super hard problems. Okay, at least generate an estimate for the answer. Okay, and believe me, there are hard problems in physics, and physicists, real working physicists, very often use dimensional analysis, as I'm going to show you in a minute, with a real example, to solve problems that they simply couldn't otherwise solve. All right, so just give me a minute to erase the board, and I shall be back. Okay, so dimensional analysis is the single most powerful tool that you have in your physics toolbox for solving problems that are way too hard for you to solve otherwise, at least generating estimates for solutions. Okay, so let me give you a nice example. Suppose I asked you to estimate the pressure at the center of the sun. Okay, so first of all, you have no clue how to do that, right? I mean, that's the sort of thing that, you know, you take 4 years of undergraduate, you go to graduate school, you find, you know, there are very complex laws that govern sort of the magnetohydrodynamics, the, you know, thermodynamics, all kinds of complicated processes going on in the sun, from the nuclear fusion to, you know, radiation zone and convection zone and all kinds of crazy physics going on. And then you construct some supercomputer simulation of this thing, and you spend months and months of research on it and so on, and you get some answer, okay? So I'm going to show you how to get the answer in about 5 minutes, at least to the right order of magnitude. Okay, so what you do is you just think like a physicist, okay? So you say, I've got the sun. What does the sun look like? I don't know, it's this great big ball. It's a great big ball of, you know, mainly hydrogen and so 25% helium gas. That's on it. It's just a big ball of gas. And that gas is under pressure. And we're interested in figuring out, you know, what is the pressure at the center of the sun, at least a ballpark estimate for what it is, you know, order of magnitude. And so you might ask yourself, the first question is, well, what would the pressure at the center of the sun depend upon? What could it possibly depend upon? So P depends on, and we're going to list here some variables, some physical parameters, easily measured physical parameters that describe the sun. And so one of the first things you would think about is, well, pressure, the pressure at the center of the sun. And this is sort of the art. There's an art to doing dimensional analysis, and you get better and better at it with the more practice you have and the more physics that you understand. Okay, so you look at the sun, what could the pressure depend upon? Well, it's almost certainly going to depend upon the mass of the sun. Okay, and then, but why? You need to understand why. Well, what is causing the pressure? What's causing the pressure is every particle of you know, hydrogen or proton, electron, whatever, all the particles in the sun, every particle is attracting every other particle. And you know that and that's what's causing the pressure. Okay, and so the gravitational force between two masses depends upon the mass. Okay, so the more mass that's present in a given region of space, the stronger the gravitational forces will be, and hence the greater the pressure. So it's certainly going to depend upon the mass. If you increase the mass for a given volume, the pressure is going to increase. So in your formula for pressure, it's going to involve the mass m, and the mass m is going to be in the numerator of that formula. Okay, you can guess that right away. Okay. It might be m, it might be m squared, you don't know. Okay, but it's going to be in the numerator. When you increase the mass for a given size, the pressure is going to go up. Another thing it might depend upon is the radius of the sun, how big the sun is. Okay, so radius. And why is that? Well, you know that the gravitational force between two masses is g times m1 times m2 divided by the distance squared. So if the particles are closer together, the gravitational forces are stronger, the pressure will be larger. So you would expect, if you were to take the same mass of gas and have it compressed into a smaller volume, all the particles are closer together, gravitational forces are stronger, pressure is greater. So you would expect the pressure to increase as the radius decreases, which means that R should be in the denominator of your final expression for the pressure in terms of these variables. And then something else, let's see. We're talking about all these gravitational forces. Well, those gravitational forces, the basic law of physics is F is equal to g m1m2 over r squared. We've got the m dependence, we've got the r dependence, but we have no g. G is Newton's universal gravitational constant. If you were to double, if we lived in a universe with a double Newton's gravitational constant, all the gravitational forces would be doubly strong, and so then the pressure for a given m and r would be larger. And so it must also depend upon g. And again, if g is bigger, gravitational forces are stronger, pressure is larger, so g in your formula, g is probably going to be in the numerator. You don't know whether it's g squared or g cubed or whatever, but it's something. So then these are three variables here. And then you say, okay, great. Pressure depends upon these in some way. So you're going to get some algebraic expression involving these three variables. And so first of all, we're using dimensional analysis to solve this problem. Okay, so the dimensions of pressure are, well, pressure is a force per unit area. Okay, and the dimensions of force, we figured out last time, is mass times length over time squared, and then area is a length squared. Okay, so the dimensions of pressure are mass, and then the length up here, the length squared down there, you have a length time squared. So the dimensions of pressure are mass over length times squared. Okay, or in units, newtons per square meter. Okay, so then we say somehow we need to combine m, r, and g in some algebraic formula that will have the dimensions of pressure, mass over length times squared. So we don't know the answer, so we'll say, okay, we'll say that pressure is proportional to, let's say, mass to some unknown power a, the radius of the sun to some unknown power b, times Newton's gravitational constant to some unknown power c. Okay, so what we're trying to do is use dimensional analysis to solve for these unknown powers a, b, and c. Okay, so the way that we do this is, given this expression, proportional means up to some unknown numerical factor without dimensions. It could be a half here, it could be a 2, it could be a pi, whatever, something like that, doesn't matter. Okay, so the dimensions of pressure, according to this formula, the dimensions of pressure are going to be the dimensions of mass, which is m, to the power of a. If that were mass squared, the dimensions of mass squared is m squared. Okay, the radius of the sun is to the power of b, so the dimensions of r to the b will be a length to the power of b. And then you have Newton's gravitational constant to some unknown power c. The dimensions for Newton's gravitational constant, we derived that last time, length cubed over mass times squared. Okay, so this is a length cubed over mass times squared to the unknown power c. Okay, so then you crank this out and you say, and you just treat this as an algebraic expression. You have an m to the power of a there, you have an m to the power of c in the denominator. So the masses, the power of the masses is a minus c. Okay, and then you have a length. There's a b there, and there's a 3c there. So it's length to the power of b plus 3c. And then there is a time to the power of, it's 2 in the denominator, it's 2c in the denominator, so negative 2c. Okay? So if this formula is correct, then the dimensions of the right-hand side of this formula are this. Now those dimensions better equal this. Okay? And so this is mass to the power 1. This is a length to the power of negative 1, and a time to the power of negative 2. Okay? And so then you have 3 equations and 3 unknowns. It must be true that a minus c is 1, b plus 3c is minus 1, and minus 2c is minus 2. Okay, so this is really easy to solve for. So we say, immediately we can read off, well, minus 2c is minus 2, so c is equal to 1. And then if c is equal to 1, we have a minus 1 is equal to 1. And so a is equal to 2. And then B, so B is going to be, there's a length minus 1 there, so B is going to be minus 1 minus 3C, which is minus 4. Okay, and so what we get, and let me write it down over here, so what we get is that the pressure at the center of the sun is proportional to the mass of the sun. Let's put G first. So it's G to the power of C, C is equal to 1, times mass to the power of A is equal to 2, so it's mass squared, and then it's radius to the power of B, that's to the power of minus 4, so it's R to the power of plus 4 in the denominator. And so you can just double check then. What your sort of physics intuition said is that, yeah, if we increase the mass for a given radius and Newton's gravitational constant, stronger gravitational forces, pressures increase. So mass should be in the numerator. In fact, it goes up like mass squared. If you double the mass, if keeping everything else the same, you quadruple the pressure at the center of the sun. Okay? And it depends, in the numerator there's G. If you double the strength of gravity, you double the pressure. This is the most interesting, R to the power 4 in the denominator. If you take the sun with a given mass and a given radius and a given Newton's gravitational constant, and you were to compress that sun to 1/2 of its radius, 1/2 to the power of 4, 2 times 2 is 4 times 2 is 8 times 16. The pressure would increase by a factor of 16 if you made the sun half of the radius. So that is an amazing amount of information that you have gleaned about the physics of this problem with very, very little work. Okay? And it's very important that this is a proportionality. We don't know the numerical factor in front here. Okay, it could be a half, it could be any dimensionless numerical constant. This analysis is very rough. It'll give you a rough order of magnitude estimate of the answer, but you might be out by a factor of pi or 2 or 7 or whatever. It is highly unlikely that you were out by a factor of 1,000,000. It's not like pressure is equal to 1,000,000 times this thing. It's usually some number of order of magnitude 1. So I'm expecting that you understand this concept of order of magnitude, like power of 10. Okay. So great. So this is fantastic. Okay. So then let's see if this actually works. Okay. So let's just write it out over here. So I got some numbers over here. Okay. So let's stick in some numbers into this formula. So pressure at the center of the sun, according to this relationship here, will be of the order of magnitude. So a single squiggly line there means this thing is of the order of magnitude, like to the nearest power of 10. Is it 10 squared? Is it 10 to the 100? Is it 10 to the minus 2? What power of 10 is it? Okay, it's of this order of magnitude. So now let's plug in some numbers. So we know what G is. So whenever you're plugging numbers into these things here, because you're only interested in powers of 10, at most you use one significant figure. Okay, so Newton's gravitational constant with one significant figure is 7 times 10 to the minus 11, I think, meters cubed over kilogram second squared. Okay, and this thing is just to the power of 1 times mass squared. So the mass of the sun is 2 times 10 to the 30 kilograms. Okay, that's easily determined by just taking an object and letting it float around the sun like the Earth, and then using Kepler's law. Okay, so that's that, and then we square that thing, and then we divide that by the radius of the sun to the power of 4, and that's easily measured as well. So that's 7 times 10 to the 8 meters. We take that to the power of 4, and we work out those numbers. And remember that we only expect this answer to give us a ballpark estimate. So we only write down powers of 10. We forget this is a number with 1 sig fig. If you just write 10 to the minus 11, that's 0 sig figs. So we're basically writing the answer to 0 sig figs. Okay, and so when you crank this out, you get like 10 to the 15. Okay, and the units here work out, of course, to be newtons per square meter. Okay, force per unit area, that's pressure. Okay, so there's your answer, 10 to the 15 newtons per square meter. Okay, so then you ask, you're not done, okay? So that's the answer. But then you have to, this is a super important thing to do in any physics problem. When you get an answer, you need to ask, Well, how big is that? Is that a big number? Is that a small number? Well, I don't know. It's 10 to the 15. It could be small. It's small compared to the pressure at the center of a neutron star or something like that. You know, but whatever, or it's large compared to something else. So let's compare. What is the sun? What is the sun? It's a big ball of gas. So it's gas under pressure. What gas are we familiar with that's under pressure? Well, the atmosphere. Okay, what's the pressure? What's atmospheric pressure? Well, it's 100,000 newtons per square meter, so 10 to the 5. So this is of the order of magnitude of 10 to the 10 atmospheres. Okay, 10 to the 10 is 10 billion. So the pressure at the center of the sun, according to our super simple dimensional analysis argument, okay, suggests that the pressure at the center of the sun is on the order of magnitude of 10 billion times the pressure of the air around us right now. That's pretty high pressure, okay? That's pretty cool, okay? So then you might wonder, is this even right? Is this even close? Well, like I said at the beginning, so then, you do your undergraduate degree, and then you go to in astrophysics and stuff, and then you take all these advanced courses in, magnetohydrodynamics and thermodynamics and fluid flows and all kinds of crazy stuff, how radiation energy flows and so on. And then you come up with an answer, and it's basically the same answer here, okay, with some slightly different numerical factor in front. Okay, so what this tells you is that dimensional analysis is an extremely powerful tool in your toolkit. So like I said, very often physicists come across problems that are just too hard to solve. And so what they do is they make estimates. Okay, they say, well, the answer, I don't know what the answer is, but I know it should depend upon these sorts of variables, because I can imagine, okay, physics really involves a deep understanding and a deep intuition about how the world works. I can imagine if I, shrink the sun smaller, that's going to increase the pressure. Okay, if I, increase the mass for the same radius, well, that's going to increase the pressure and so on. So you can figure out just sort of the art of figuring out what sort of variables in the problem your answer will depend upon. And then just do a simple dimensional analysis, and bang, there it is. Plug in some numbers, and you will get an answer that is probably within the right ballpark rough order of magnitude. It's absolutely amazing. This is a super important skill that you should start learning in 121 now, and you're going to be applying it over and over again in your future courses. Super cool stuff. Okay, I'm just going to erase the board, and I'll give you another sort of more down-to-earth example. All right. Good. Okay, so I'd like to give you a little bit more of a down-to-earth example of the power of dimensional analysis. And so we're going to look at drag force. Okay, so the example that we're going to have in mind is a car. So you have this car, and it's driving down the road with some speed v to the right. And of course there's wind. So the car is pushing air out of the way. So there used to be air here, now the car is there. So the air has to be pushed out of the way. And air has mass. It has a lot more mass than you usually think. I think it's about a kilogram per cubic meter, something like that. So as the car is driving, you're always pushing this air out of the way, and that takes work. It takes, force through distance takes work, and there's friction involved and so on. And so, so there's going to be a drag force. So the drag force acts on the car backwards. So the drag force retards the motion. So if you're driving down the road and you put the car in neutral, then the car will slow down due to the drag force. Okay, so now what we want to do is we want to figure out, just using dimensional analysis, we want to figure out what that drag force depends upon. We want to find an algebraic formula that gives us an expression, an estimate for the drag force. So the drag force depends on certain parameters that describe this physical system. And so again, here's where the art of doing dimensional analysis comes in. So it's not something that you have immediately, but it comes with a deeper understanding of physics and just practice, practice, practice. Okay, so the first thing you think about is, well, when this car goes faster, there's going to be a greater drag force. So clearly it's going to depend upon the speed of the car. And it might be proportional to the speed, might be proportional to the square of the speed, the cube of the speed, you don't know. But you do know that v is going to be in the numerator. So the bigger the speed, the bigger the drag force. Okay, and then something else that it might depend on is, you think about a vehicle, say a big transport truck. It has a large surface area, presented to to the air. So it's so every meter it moves forward, it moves a lot of air out of the way. But if you have a low, sleek, streamlined kind of sports car, then the surface area, looking head on, what's the surface area? What's the cross section of the car? So just sort of a cross section of the car. There's a surface area. So clearly, if you increase the surface area, then you're going to be increasing the drag force. So it should depend also upon the cross-sectional area, the largest cross-sectional area of the car. Ignoring the streamlining of the car, just look at the car and take kind of like a silhouette of the car. What's the area that it presents perpendicular to its motion? So that's also going to be in the numerator of your final algebraic expression for the drag force. The bigger the area, the bigger the drag force, right? That's sort of common sense. And something else, though. It should depend upon something to do with the air. So basically, as the car drives, it needs to move the mass of the air out of the way. And so if the air is more dense, then it's going to be having to move more mass, a greater rate of mass being pushed aside. So it's going to depend upon the density of the fluid that it moves through. I mean, think of this thing moving through water compared to air. There'll be a lot more drag force moving through water. So it's going to depend upon the density of the air. And the density is given the Greek symbol rho, so that's kilograms per cubic meter. And again, the greater the density, the greater the drag force. So this is also going to appear in the numerator to some power. Okay, so we don't know what those powers are. And then we say, okay, so let's try to figure out what combination of these variables will give you something with the correct dimensions of force, drag force. Okay, so let's go down here. So first of all, we figure out the dimensions of the drag force. The dimensions of drag force, remember, I don't remember what they are, but I just think, well, force is mass times acceleration. Okay, and so it's going to be a mass, and then the acceleration is a length over time squared. So we need some combination of these three variables, which will give the dimensions of mass times length over time squared. So, so let's work out the dimensions of each of these individually. The dimensions of velocity is a length over time. The dimensions of cross-sectional area is length squared, and the dimensions of rho, the density of air, is a mass per unit volume. So the dimensions of rho is a mass per unit volume. Okay, so we have that. And then what you do is you can do this algebraically, or you can just sort of think about it in simple cases like this. So, sort of an algorithm for getting at the solution is you set the drag force to be proportional to, remember that dimensional analysis can't tell you a dimensionless proportionality constant in front. So it's proportional to, it's some dimensionless numerical factor times, let's say, what order should we do this? So let's put the density to some unknown power A, and then the area to some unknown power B, and then the velocity to some unknown power C. Okay, and then you just plug in these dimensions, length over time to the power of A, length squared to the power of B, and, mass over length cubed to the power of A, length squared to the power of B, and length over time to the power of C, and then you get three equations in three unknowns for the unknown coefficients A, B, and C. So I'll leave that as an exercise for you to do. But you can also just do this sort of just by thinking about it. You can say, well, I want the force in the end to have our expression of the dimensions of mass, length over time squared. And if we look at these quantities here, we can see that there's a mass only in this row and not in the area and the velocity. And so rho must appear to linear power. So it's rho to the power 1. That m will give you that m. But you'll have an extra length cubed. And so you have to get rid of that length cubed by maybe multiplying by the area. And so that'll give you mass over length cubed times length squared is mass over length. Okay, and then you can say v squared. You can see v squared is length squared over time squared multiplied by what we had before will give you mass length over time squared. So you can also just sort of eyeball it, as you get better at this and figure it out. But anyways, we can see that the force is proportional to this. And if you work it out, you get that the drag force is proportional to, you can also write that as, is equal to some unknown dimensionless constant. In this case, it's called the drag coefficient, which depends upon how streamlined the vehicle is. and then it's proportional to the density to the power of 1, the cross-sectional area to the power of 1, and the speed squared. Okay, so that's what you get. So this particular combination of these three variables has the dimensions of force, and so you've determined the drag, an expression, an estimate for the drag force up to an unknown proportionality constant, the drag coefficient. And that drag coefficient is on the order of magnitude of 1. Like, so for a very streamlined car, it might be 0.7, you know, for a big transport truck, it might be bigger, and so on, but it's something on the order of magnitude of 1. Okay, so this is really quite remarkable. So first of all, it agrees with your intuition that, yeah, if you increase the density of the fluid you're moving through, the drag force will increase the cross-sectional area, the drag force will increase. But this is the most interesting one. So what it tells you is that the drag force, this particular form of drag force, depends upon the square of the speed. So if you double the speed from going 50 kilometers per hour in the city to 100 kilometers per hour on a highway, then if you double V, you quadruple the drag force. Okay, so that's a really interesting thing to know about drag force. I mean, think about gas mileage. You've quadrupled the drag force. And that sort of deeper sort of insight, physical insight into this situation comes from simple dimensional analysis like this. You know, I'll also add that you can get more complicated. If there is an additional parameter associated with the fluid, say viscosity. So viscosity is, did I spell viscosity right? Yes. So if you have viscosity, let's give it a symbol B. That's a property of air, having to do with how layers of air sort of move against each other and provide friction against each other. So if the fluid has some viscosity, then B will have the dimensions that you'll have a drag force term which is proportional to the viscosity times the speed. So you'll have a term linear in the speed, and then there'll be a term quadratic in the speed, and so on. Okay, so but the power of dimensional analysis is quite remarkable. So I just want to sort of wrap up and just the power of dimensional analysis. So I'll just remind you, there are basically two main ways in which you use it. One is when you're working out numerical solutions. So you have a formula and you're plugging numbers in, and when you're plugging numbers into the formula, you always write down the units and make sure that the units cancel out in such a way that you get the right units for the final answer. As I said, that's something I expect you to be in a habit of already from high school. Okay, but then we're going to extend that to the fact that, you know, most of the solutions that you're going to be working out in this physics course are going to be algebraic solutions. And so without plugging numbers in, you need to think in terms of dimensions, mass, length, and time, and make sure that, you know, do algebraic manipulations to make sure that dimensions come out right. So this is for algebraic solutions. So this is a great way, either numerical or algebraic, to check your solutions, to check that you haven't made an obvious mistake. But the real power of dimensional analysis is, as I said before, solving hard problems. Okay, in order to solve this sort of a problem, it would require, you know, a pretty detailed knowledge. To solve this in detail would require, an in-depth knowledge of, you know, flows of fluids, laminar flow, turbulence, all kinds of crazy physics is involved in something as simple as drag force. But you can get an estimate of the order of magnitude of the effect just by simple dimensional analysis. Very powerful tool. Really try to use it. So one of your rocket science activities is devoted to dimensional analysis, to really encourage you to start thinking like a physicist and using that very powerful tool in your physics problem solving. Okay.